So good morning, everyone. It's a pleasure to have Reinhold here with us today. Do you hear me properly? Okay, so Reinhold is, he did his PhD in the University of Stuttgart, and then he was a faculty at the University of Freiburg. Now he is a full professor at the Düsseldorf University. He's a condensed matter physicist, and he works with topological phases of matter. He typically visits the institute every year, I hear, and he's visiting us this month. It's a pleasure to have him here, and in particular today giving a seminar about his work. So thank you, Reinhold, for being here, and the stage is yours.
Thank you for the introduction. And as always, it's a great pleasure to be back to Natal. It feels like coming home every time I come here and visit the Institute. So today I want to speak about a rather hot topic, quantum Mpemba effects. I do not assume you know anything about Mpemba effects, so I will first introduce what is or what are Mpemba effects, and then discuss our theory of quantum Mpemba effects in open quantum systems. This is based on work with Andrea Nava, who is a postdoc in my group, which appeared in a PRL last year. I will give 3 examples from condensed matter theory for how to implement or how to probe this type of theory in experiments. And then I want to take you on a fishing trip with Aristotle when we discuss the Pontus Mpemba effect that's based on this PRL, which will come out next week, also with Andrea Nava. And some of the applications here are based on 2 other papers. So let's get started. The classical Mpemba effect goes actually all the way back to Aristotle. So 2,300 something years ago, Aristotle, in one of his famous books, he stated the fact that water has been previously warmed contributes to its freezing quicker. So in other words, by first heating up cold water and then freezing it, it might freeze quicker than if you just freeze the cold water from the outset. So it's a counterintuitive phenomenon. Not naturally, you would expect that cold water will also approach the ice state quicker, but by heating it up first, by putting it in the sun, it can freeze quicker. That's the Mpemba effect, as we call it now. The effect got, as usual in science, effects tend to get forgotten, overlooked, and it disappeared from public memory, and it got rediscovered independently by 3 people after the Middle Ages: Giovanni Mariani, Francis Bacon, and René Descartes, and then of course it got forgotten again. Until 1963, Erasto Mpemba, and that's why the effect is now named Mpemba effect. He was back then a 13-year-old high school student in Tanzania, and these high school students were given the exercise of taking ice cream mix, which was a sort of fluid, and making ice cream out of it as quickly as possible. And so all his schoolmates ran to the fridge, put it in. He was too slow, and so his ice cream mix actually heated up. And only when the others put it out, he put his ice cream mix in and realized it was freezing much quicker than the one of the other high school students. So that's how he got into this effect, and he suspected then that there's a deeper principle behind. He paired up with a professor, Osborne, who was at the university there, and they wrote a famous paper then in 1979. These other 2 gentlemen, both have passed away since, but they were basically the ones who discovered this effect and then looked systematically at it in water. Actually, in water, it's quite difficult because water has such a complicated structure, and it's very difficult to really nail down the Mpemba effect in water, but we will see there are simpler models where you can see it. So let's formalize this in the simplest case when we have let's say, a classical system, and let's compare two system copies. One we prepare at some hotter temperature, T hot, one at a colder temperature, T cold. And then we put both of them into the fridge. Let's say we rapidly quench the temperature to a final temperature, TF, like the temperature of the fridge, which is below both of these temperatures. And then the question is, so you have a control parameter, which is temperature, which you rapidly quench. I should say it's important that you do this rapidly. If you do it slowly, you will never get this Mpemba effect. It's really linked to a quench, to a rapid change of parameters. And then when you do this, you measure the relaxation time of the respective copy towards the final steady state that has then reached this temperature TF. Yeah, this will take some time. Even though you have changed rapidly the temperature, the system needs time to adjust to this new parameter, and so it will take a relaxation time tau hot for the initial state with the temperature. Oh, this doesn't work anymore. With the temperature T hot, and another time for T cold. Yeah, and we say there is a Mpemba effect if the hot system relaxes faster than the cold system. Yeah. Oh, okay. So if the hot system has a shorter relaxation time than the cold system, then we say there is a Mpemba effect or a thermal Mpemba effect. The hot system cools down faster than the cold one. So my postdoc Andrea Nava back then was a postdoc in CISA of Michele Fabrizio, and he proposed the first quantum generalization of this effect, so that such an effect could also happen in quantum systems. And this has then been very intensely pursued. Pasquale Calabrese from CISA is one of the leading figures in this game, and they've also experiments on ion traps have been done in Innsbruck and other labs at Weizmann Institute. And there's a nice review if you want to read on these available experiments already that see quantum Mpemba effects in real ion trap experiments. Of course, this effect is not just a theoretical curiosity, it also has very practical applications because you can use it to speed up systematically certain processes like quantum state preparation or quantum cooling. So there is also an interesting application side to it. So the classical Mpemba effect was quantitatively described in a seminal paper by Liu and Ratz in 2017. And they showed that the thermal Mpemba effect in classical systems can be related to the geometrical properties of the free energy landscape of your system. In particular, if you do a quench, then there might be shortcuts in the energy landscape that allow a system, even though it has a nominally unfavorable initial state, to relax quicker to the final steady state. And in the quantitative description, which they did for Markovian systems, so for systems that are coupled to some reservoir that has basically zero memory time, very short memory time. So then we speak of a Markovian or memory-less system. And they showed that here it's critical to introduce a so-called distance from equilibrium function in a state space. So you have a distribution function for your system, and this distribution function after the quench will relax to the steady state. And you need to somehow quantify how far away is this steady state distribution from the final one. So this will also play a key role in our approach for quantum Mpemba effects. So let's now come to quantum Mpemba effects in open quantum systems. Open means the quantum system of interest can be coupled to reservoirs. So to heat baths, to measurement devices, the reservoirs can be fermions or bosons, whatever you want, but we assume weak coupling, and we assume that the reservoirs are Markovian. Yeah, we can talk about non-Markovian later, but here we discuss the Markovian case and under certain approximations that are well known, wideband approximation for the leads, for the reservoirs, and a rotating wave approximation. It's then known that the quantum mechanical system state, rho of t, which is the density operator as a function of time, evolves according to the famous Lindblad equation. So how does this Lindblad equation look like? The time derivative of rho has a term that is unitary dynamics from a system Hamiltonian H, and it has dissipative contributions that are encoded in this dissipator superoperator. So D for a jump operator L acts on rho like L rho L dagger minus 1/2 the anti-commutator of L dagger L with rho. And this part here describes the effects, the dissipative effects of the reservoirs. Yeah? And you can couple here several reservoirs or just one, whatever you want. These LMN are now jump operators that bring you from many-body state N of your system to state M with some transition rate gamma Mn due to the coupling to these reservoirs. And usually you compute these transition rates using Fermi's golden rule, yeah, because it's weak coupling. So this whole right side we can view as a super operator M, which acts on the density operator. Yeah? So that's the Lindblad master equation. You see that rho dot is expressed only as a function of rho of t. Yeah? That's because we have a Markovian system. How do you solve such a Lindblad equation numerically or in practice, also perhaps also analytically? Typically the approach is to vectorize it. So this n by n, let's say we have an n-dimensional system space, a Hilbert space of n dimensions, then the density matrix is n square, is n by n, so you can arrange it as an n square dimensional vector indicated with this hat. Yeah, and the super operator in this vectorized representation becomes a n square by n square matrix, which has eigenvalues lambda beta that can be complex. And since this super operator is not in general Hermitian, you need to distinguish the right and left eigenvectors for the given eigenvalue lambda beta. So right and left eigenvectors. And once you have diagonalized this super operator, this matrix M, you can write the solution of the Lindblad equation, which is now just a linear algebra problem, in this form. So the time-dependent density operator follows from some initial density operator via this formula. All the time dependence sits in these e to the lambda t factors. Yeah. So all the real parts of these eigenvalues have to be non-positive. If they were positive, the thing would blow up and the unit normalization of the trace is not possible anymore. There is in fact at least one eigenvalue which is 0, and that's the steady state. At time to infinity, the system approaches a steady state corresponding either to an equilibrium steady state, if you have just one reservoir or many reservoirs all with the same parameters, or a non-equilibrium steady state, if you have at least two reservoirs with, let's say, different chemical potentials or different temperatures, and then heat or particle currents can flow through the system, and then it's a non-equilibrium steady state. So that's described by the 0 eigenvalue. And if the eigenvalues have imaginary parts, then you have damped oscillations, a spiral motion towards the steady state. Okay. Let's give a first example for this type of Lindblad approach, and then I will describe what we do to see quantum Mpemba effects for it. This example is an interacting minimal Kitaev model. So if you know the Kitaev chain as a model for topological superconductors and Majorana bound states, this is just a chain with two sides. Yeah, that's the minimal one. The two sides are two quantum dots, 1 and 2, So these are sites where fermions can live, and the fermions are spinless, described by fermion operators C1 and C2 with occupation N1 and N2. So it's either 0 or 1 because of the Pauli principle. And the Hamiltonian of this double dot is given here. So you have on-site energies, epsilon 1 and epsilon 2. There is a Coulomb energy if you occupy both of them. There's a hopping term, TH, between these two, and there could also be a pairing term if you have the double dot on a superconductor. Yeah? Then you can exchange Cooper pairs and thereby change the occupation in 2 units. So this is this model. We connect it by tunnel amplitudes to the right and left leads, and the leads are just metals, free fermions described by Fermi distribution. So you have to specify chemical potentials, μL, μR, and temperatures, T left and TR. And the difference μL minus μR is the applied voltage. Okay. Why did we choose this model? I mean, it looks a bit special, but the point is that it has recently been realized experimentally in a pursuit of so-called poor man's Majorana fermions. So these Majorana bound states are usually topologically protected. They emerge at the ends of the Kitaev chain if you make the chain long. If it's just 2 sides, there is no topological protection, but you can fine-tune parameters such that on dot 1 there is a Majorana and on dot 2 is a Majorana. It's just not robust against changes in the parameters. That's why it's called a poor man Majorana, but other than that, it has all the properties of Majorana states. And so this model has been realized in Delft in the group of Leo Kauvenhoven, and we here point out that it's also a nice model to study the quantum Mpemba effect. So for simplicity here, we choose these tunnel couplings such that the hybridization energies, so the scales for coupling the dots to the leads, so alpha determines the lead index left or right, I is the dot index 1 or 2. So these hybridizations are from Fermi's golden rule 2 pi times density of states in the lead, and then the absolute square of this respective tunnel amplitude. And we parameterize them in terms of an overall system lead coupling, capital gamma, and a geometric angle theta. So if theta is 0, you have a linear arrangement. Then dot 1 couples only to the left lead, dot 2 couples only to the right lead. While if you have theta pi half, then you have basically an interference ring. Yeah? Then these are the 2 extreme cases, but of course you can vary theta in arbitrary ways. Okay, so that's the model. And we will describe it using the Lindblad approach. And now let me describe what you do in a Mpemba protocol. So again, we consider a rapid change of control parameters. And these have to be experimentally accessible. Let's denote them by P. For instance, these P include the temperatures or chemical potentials of the leads. Yeah, these you can easily change. Again, as I said, there's no Mpemba physics if you just change these very slowly. So what we do is a quench at times before 0. We have pre-quench parameters. After the time 0, at time 0, we have the quench. And then we change these parameters to the final values, which are the post-quench parameters. And they will determine your steady state, either non-equilibrium or equilibrium, which will be reached at long times, and again this state may carry a current if you have 2 reservoirs. So we extend this cold versus hot initial temperature to close versus far initial conditions. So we say PC is a control parameter set that is close to the post-quench set, and PF is one that is far, and in order to do so we need to have a distance function in parameter space. Here we just choose a Euclidean distance, so that's given here. So you basically define it in such a way, and then of course for the closed system the distance is shorter than for the far system. And as long as you preserve the parameter ordering the precise definition of this distance function is irrelevant. Yeah, you can change it. We just took this. What is more important is now the distance function in Hilbert space, in state space. That's the critical issue, and this was also emphasized very much by Liu and Ratz. And because people didn't pay attention to this important fact, there are many papers in the literature that claim Mpemba effects where actually nothing happened and the other way around. Yeah? So you really have to be careful how you define this distance function. And as Liu and Ratz, emphasized, such a distance function, the t of rho of t, which measures the distance of rho of t to the final non-equilibrium or equilibrium steady state density operator. This function, as a function of time, must be continuous, monotonically non-increasing, and convex. And only if you satisfy these three conditions, you are guaranteed that you properly monitor or detect quantum Mpemba effects. Otherwise, if you use other devices to measure the distance, like people have used the diagonal elements of the density operator or so, but then there is the possibility or the danger that you have a false detection. So here we use the trace distance, which is defined here. So it's basically the absolute value of rho of t minus rho steady state, and this trace distance satisfies all these criteria under Markovian Lindblad dynamics. Yeah, this one can show. This is not unique. There are also other distance measures like the Bour's distance, which is related to the fidelity, or the quantum relative entropy. They also can be used and they will give you the same answers. Yeah, whether there is Mpemba or not doesn't matter which distance measure you take, as long as it satisfies these criteria, it will give the same answer at the end. We just use this one for its operational relevance in quantum information theory. Now, usually, if you want to measure this beast in an actual experiment, you have to do quantum state tomography, which is expensive. But fortunately, there are often more accessible observables that allow you to diagnose the quantum Mpemba effect, and I will come to that. But sort of in a strict sense, you have to go through this route. So given this distance function, you can now distinguish two types of quantum Mpemba effects. The first one is the type 1, and this one occurs because the initial state in state space, so rho of t equals 0, for the far system, so for the nominally unfavorable system where Pf is the parameter set, is actually closer to the steady state. So you have the trace distance of rho f of 0, and then also for all subsequent times, is actually below the one for the nominally closed system. It could well be that the parameters look unfavorable, but the actual state is closer to the steady state. And so if this happens, we speak of a type 1 quantum Mpemba effect. This is sort of not so surprising. What is more surprising is the type 2. This happens even though also the initial state is at a disadvantage. So also the distance initially in state space is bigger for the far system. So not only the parameter distance, but also the state distance is bigger. But then what can happen is that as a function of time, at some finite t star, there is a crossing point between these two trace distance curves, and then at long times, this nominally far system relaxes quicker to the steady state. And that's this more elusive type 2 quantum Mpemba effect. And we will now see that in this Poorman-Kitaev model, you have all three possibilities: no Mpemba, type 1, and type 2. So to see this, we first write the system Hamiltonian in the many-body basis. There are 4 many-body states for this double dot. Either you have no electron in the system, or one on dot 1, or one on dot 2, or doubly occupied. And in this basis, the Hamiltonian is just a 4×4 matrix. And you see that the states with even parity, which is 0 and d, so there are an even number of fermions in it, decouples, so it's just this, these entries, it decouples from the odd parity states 1 and 2. So the Hamiltonian has a dynamics that only works in a given parity sector. While the transition rates, so the dissipative part in the Lindblad equation, and these transition rates now come as a sum from the left and right transition rates, which you compute from Fermi's golden rule, and they describe the injection or removal of a single electron in your system. So if you change the occupation of the system by 1 electron, you must mix the parities. Yeah? You go from even to odd parity. So we have an interesting competition between unitary and dissipative dynamics here. And now what we do here is we fix most of the parameters at these values and consider quenching only the reservoir parameters, temperature and chemical potential of the left lead from the initial value given in this plane to the final value, which will be equal to the one of the right one. So the final steady state is an equilibrium steady state. This is this point in the plane. Okay? So let's say if we start at this point, we will have a relaxation time that lives on this isoline. So the lines here are isolines of the relaxation time, which we get by computing the trace distance and measuring the relaxation time for each of these TL and mu-L. And then we plot them on a color scale. So red means it has a high, it's low, so it has a high relaxation time. Blue means it relaxes very fast. Yeah, so if you compare these two yellow stars, you see they are both on an isoline. This yellow star in parameter space is much closer to this than this one. Yeah, they lie on the line, so you can directly see this one is further away than this one. But still they have the same relaxation time. Or this blue star, you see, has a higher relaxation time. So it will take longer to relax to this than both these states. And if we now compare these two states, we see that this yellow star has a shorter relaxation time, but is further away. So there is clearly a Mpemba effect if we compare these two initial states here. Yeah, so that's explained here again. So the blue star initial state needs a longer relaxation time than this one, but it's closer to the final state, so it's clear there is a Mpemba effect if we compare these two. Yes?
Distance that you choose, you predict at the same crossing point?
What do you mean by crossing point?
For example, here you are taking the trace distance, right?
Yes.
And then let's say that the warmer body has to cross with the hot body, right?
Not necessarily. I haven't said whether it's type 1 or type 2. This you cannot tell from this plot yet. I will come now in the next slide to the actual dynamics of the trace distance.
I see, but this will not depend on the
This will not depend on the measure. So the precise T star might depend on the measure, but whether it's type 1 or type 2 will not depend on the measure.
Thanks.
So now to really see whether it's type 1 or type 2, you have to go for this calculation of the trace distance. So this plot shows you this is on a logarithmic scale. This is the trace distance versus temperature. So here is the quench, and here in this direction we approach the steady state. So ultimately the trace distance goes to 0 because the state relaxes to the steady state. And in the main panel, so here we consider different parameter choices. The yellow curves are always for far initial states in terms of the Euclidean distance. The blue curve means the pre-quench parameters are closer to the final ones. Yeah, so in this case, we see that the initial state is also far because the yellow curve is on top of the blue one. But then there is a crossing, so this would be this T star, and then eventually there is an exponential enhancement of the relaxation time for the system that has been far, both in terms of state space and in terms of Euclidean state space. So this is type 2 quantum Mpemba, you have a crossing of these two trace distance curves. The left lower panel here shows that the yellow curve is actually always below the blue curve. So the far initial state is always quicker to relax to the final state. So that's type 1, while here that's what you would expect. The closed state also relaxes quicker. That's no Mpemba. Yeah, so you can have all three possibilities in this model. As I said, measuring a trace distance in actual experiments is a challenge. Not impossible, but it's difficult. It requires state tomography. Fortunately, there are simpler observables that can already tell you whether there is a Mpemba effect or not. It cannot tell you then which type, but at least it can tell you Mpemba or not. For instance, the time-dependent currents through the device. So here we show the absolute value of the current with respect to the final value. For this case, the final value is 0 because it's an equilibrium steady state, and the dashed and solid lines refer to the current from the left lead to the center and from the center to the right lead. Eventually, they all converge to the same. And you see here the far system relaxes quicker in the main panel, so there is a Mpemba effect. But you cannot tell from the panel whether it's type 1 or type 2. By looking at the trace distance, you can determine it's type 1. While in the inset, you see it's no quantum Mpemba effect. Yeah. So example 2 is the famous Anderson impurity model. So in this case, you consider just a spinful interacting single level dot, which you can fill with spin up or spin down electrons and couple to two metallic leads. And so the system is just this Anderson impurity characterized with some energy epsilon and the on-site energy U due to Coulomb repulsion if you put two electrons on this side. In this case, the jump operators in the Lindblad equation mix all the many-body states. That's different from the model before. And as a consequence, the equations for the diagonal states of the density operator decouple from the ones for the off-diagonal ones. And then you can work with a simpler form of the Lindblad equation, focusing just on the diagonal elements, the so-called populations. So they are contained in this vector P, which has the diagonal elements of the density operator, and these obey a decoupled equation of motion, which is just a matrix, a linear algebra equation, the so-called Pauli master equation. And again, this matrix M contains the golden rule rates. And here we see a phase diagram for a set of parameters. The system is driven to a final equilibrium steady state where both temperatures and chemical potentials are fixed. We have a reference initial state 2 with these parameters, and we fix also the pre-quench parameters for the temperature. And now we monitor what is happening as we vary the pre-quench chemical potentials of both leads. And then you get a phase diagram like that. The blue regions mean there is no Mpemba effect. These regions, the yellow regions mean there's a type 1, and these orange regions mean type 2 Mpemba effect. Yeah, so again, in the simple Anderson impurity model, you will find all three possibilities. The elusive type 2 is the most difficult to find naturally, but in principle, all three behaviors occur. And the final example I want to give for that is a superconducting weak link, in which case we quench the superconducting phase difference across a Josephson junction. So the Josephson junction is here. So this is a weak link, just a single channel, a transport channel, and coupled to a quantum dot in between, such that you can tune the transmission probability of this weak link. And you put this in a loop, which is threaded by a magnetic flux. And we have an average magnetic flux, phi naught. and a fluctuating component because we couple this to a LC circuit, a microwave environment, in order to have transitions between different levels. And so what you do in the quantum Mpemba protocol is you quench the magnetic field piercing the flux. So you change the phase difference across this junction and look for the relaxation towards the steady state. And just focus here on the left column, which is for 3 different transparencies or transmission amplitudes. This is a rather low transmission amplitude, intermediate, and very high transmission amplitude. And what we show here is again this relaxation time extracted from the trace distance on a color scale. So red means it's slow, blue means it's fast, and we show it in the plane of final, so that's the final or equilibrium phase of the steady state, and that's the pre-quench value. So if the pre-quench value is equal to the post-quench value, relaxation time is 0. That's the diagonal here, and then of course there's no relaxation, you're already in the steady state. What is surprising is that you find these perpendicular features. So there are perpendicular arcs, so open curves in this plane, in this initial final phase plane, which are sharp features, and along which the relaxation time is again very, very fast. And we can prove that we have called these Mpemba arcs in analogy to the Fermi arcs for wide semimetals. So these Mpemba arcs, these open curves, are both sufficient and necessary for having Mpemba effects in this system. And you see here, especially with high transmission probability, you have here a rich structure, and then you can realize again all 3 behaviors, no quantum Mpemba type 1 or type 2, depending on parameters. Now, in this case, what you really need to do is you have to measure the populations of so-called Andreev levels. These are levels inside the superconducting gap, and they determine basically the transport through this Josephson junction. And since you again have only a Pauli equation that governs this, you don't need a full density operator, you just need the populations. And these can be measured by microwave spectroscopy. You do not need the full state tomography, so it's much easier. So this relaxation time here would be accessible by microwave spectroscopy, which is established in many labs worldwide. And just to show you a typical example here, let's focus on this plot, which shows this trace distance as a function of time, again on a logarithmic scale here. And the target value of the phase difference is 0.7 pi. So the blue curve is the closest to this, then the orange is next, and red is furthest away from this. So if we compare now, for instance, the orange curve and the blue curve, we see this is a type 1 quantum Mpemba, because the blue curve is nominally closer but relaxes slower. If we compare the orange and the red curve, we see it's type 2 quantum Mpemba, because there is a crossing in here, and finally the state that is nominally furthest away relaxes the quickest towards this final thing, and this is connected to the existence of these Mpemba arcs. Okay, so much about the standard Mpemba protocol. Now I promise you to go fishing with Aristotle, so let's do that now. So in his book, Aristotle wrote that the fact that water has previously been warmed contributes to its freezing quickly, for so it cools sooner. Hence, many people, when they want to cool water quickly, they begin by putting it in the sun. So the inhabitants of Pontus is this region here in northern Turkey, when they encamp on the ice to fish, so back then this was way before the climate change, so the Black Sea tended to freeze in the winter, and they did ice fishing on the lake, and so they cut a hole in the ice and then fish. So the inhabitants of Pontus pour warm water around their reeds. So they basically take some water out, first warm it in the sun, and then put it around their reeds that it may freeze the quicker, for they use the ice like lead to fix the reeds. Yeah. So Aristotle really suggests a two-step optimization protocol. You start with the cold water, and your reference state would be you just put it into the water and freeze. That's system copy 1, so to speak. But system copy 2 is you first put it in the sun, heat it up, and then put it in the ice. So that's this two-step optimization protocol where you take into account the cost for heating up the warm, for heating up the water to the warm state first. This step is sort of forgotten in the standard Mpemba protocols, where you just compare different initial states. Here you start out from the same initial state, and we call this the Pontus-Mpemba effect. And let me describe this protocol, which is completely general, applies for classical or quantum systems. The quantum systems can be open or closed, Markovian or non-Markovian. It's completely general. So we consider or compare the dynamics, the non-equilibrium dynamics of two system copies. They both start in precisely the same initial state. Let's call that state S. In the Pontus example, S is the cold water, which they want to use for the just like lead. This means we can dispose of the parameter distance measure. We don't need it anymore, because both states are the same. We don't need to bother about any parameter distance measure. And also the protocol will automatically include the time cost for heating up system copy 2. So there are no hidden costs as in the standard one-step Mpemba protocols. Okay, now so system copy 1 at time 0 we perform our usual quench. So system copy 1 is subjected to a parameter quench. So it's coupled to an environment that will drive it to a target state F. That's a steady state, and in our case, in the Pontus case, this would be the ice. Yeah? So that's what you do in the direct step. That will take you a time tau S to F. Yeah? Now our other system is first put in contact to an environment that drives it to a different state, namely an auxiliary stationary state A. That would be something like the sun. So you put it in the sun in this Pontus example, and therefore the water would eventually evaporate. Yeah? If you let it evolve long enough, it will just evaporate. But let's say this in general will take a time tau SA. Of course, we shouldn't do it, wait till it has evaporated. We have to sort of interrupt this flow and at some point decouple the system from this environment and then couple it to this environment. So that's the next step. So during this time evolution toward A, once you reach some intermediate non-equilibrium state I, which would be the warm water state in Pontus, this has been reached at some time tau Si, which of course is shorter than tau Sa. At that point you decouple it from this environment, and you will then couple it in a second step to the environment, to the same environment as the direct copy. So unlike in the standard Mpemba protocol, where this hot state must also be a thermal state, here it can be a completely arbitrary non-equilibrium state. So you have more flexibility for optimization. And now in the last step you do a quench, a second quench. You couple the second system copy to the same environment as system copy 1. So it will be driven to the final steady state in some time tau I to F. And so the total two-step protocol will take the sum of these two times. And we say that the Pontus-Mpemba effect happens if the sum of these two times is shorter than the direct step. Yeah, so if by doing this two-step procedure, we are able to beat this direct step, then we have a Pontus-Mpemba effect. And this includes the time for heating up system 2. This is exactly this time tau Si. And you can systematically now optimize the time in the two-step protocol by judiciously choosing the auxiliary state A. Okay, the people in Pontus had the sun, they could not choose that, but in an experiment you might have the freedom to choose A. And you can choose the intermediate state, at which point you decouple. Yeah? And that's actually a topic for optimal control theory, so to optimize this time to the best possible time. You could also do multi-step protocols and then sort of improve it even further. So let's try to do this quantitatively again for Markovian open quantum systems described by a Lindblad equation. And here it's useful to start from a slightly different representation of the Lindblad equation, the so-called first standard form, which is given here. For an n-dimensional Markovian system, you use a positive definite Hermitian Kosakowski matrix. This has dimension n square minus 1 by times n square minus 1. So in the two-level case, n is equal to, it's a 3 by 3 matrix, a Hermitian matrix with non-negative, so positive or zero eigenvalues. And you have to specify a basis of n square minus 1 traceless operators Fn. In the n equal 2 case, these would just be the Pauli matrices. Otherwise, these are generalized Pauli matrices. And with these operators, you can write down the general Lindblad equation in first standard form like this. And the more conventionally used form that I also quoted earlier, the diagonal form follows by diagonalizing this Kosakowski matrix. It has real eigenvalues because it's Hermitian, real positive or non-negative eigenvalues. These are the transition rates, gamma j. And the jump operators Lj follow as eigenvectors from the diagonalization of this Kosakowski matrix. And the classical limit simply means that you put the Hamiltonian to 0. Then you have a purely classical system. Yeah? But the point of this exercise is that we have up to n square minus 1 to the square free real-valued dissipative parameters at our disposal. So in general, people nowadays can engineer dissipation in a way that they can sort of choose at will how this Kosakowski matrix will look like. At least in highly tunable platforms like ultra-cold atoms or ion traps, they have this freedom. And so we have up to, in the case n equal 2, up to 9 parameters that we can freely choose for parameterizing possible dissipation parameters. So it's not just the rates that are at our disposals, but the other parameters sit in the eigenvectors diagonalizing the Kosakowski matrix. Now, instead of the energy landscape that Lou and Ratz used for the thermal effect, we find it much more useful to introduce what we call a velocity field landscape. And you can understand it by associating to the density operator, which we can vectorize as a vector, rho dot. So that's the velocity field, or in vectorized form, it's a vector again. And for the Markovian Lindblad dynamics, this velocity field at time t will only depend on the density operator itself. And so that means on the jump operators and the rates. Now for the two-level case, which I will discuss in some detail, you can parameterize any state, rho of t, in terms of a Bloch vector, r of t, which has 3 components, real-valued components, and it must live inside the unit ball. If it's on the sphere, on the Bloch sphere, you have pure states. If it's inside, you have mixed states. Okay, and then the state is written like that with the vector of the 3 Pauli matrices sigma. So, and then you can visualize your quantum state nicely in the Bloch sphere. The velocity field for the two-level system can similarly be parameterized by r dot, the vector, so the time derivative of this Bloch vector. So v, and since this velocity field depends only on rho, this velocity field can only depend on the actual Bloch vector. Yeah? And what you find from the Lindblad dynamics is it has this simple form. It's some 3×3 matrix, lambda times R plus an offset vector B. And this 3×3 matrix lambda and the vector B just contain the matrix elements of the Kosakowski matrix and of the Hamiltonian. And now we use reservoir engineering ideas to choose our parameters in these matrices, or in C and H, such that the dynamics lies in the equatorial plane of the Bloch ball. So we choose it such that at all times R3 is 0, and then also the velocity stays in this equatorial plane, in the R1, R2 plane. Then we can easily visualize this velocity field. I should mention for n-state systems, there are also generalized Bloch or so-called coherence vectors that allow you to get a similar representation for the velocity field. And then you have to choose some hyperplane to illustrate the dynamics of this velocity field. But let's state with the simplest case n equal 2. There are various, so then it's a qubit, two-level system, and there are various highly tunable platforms like trapped ions, ultra-cooled atoms, or superconducting qubits, where reservoir engineering is available, and you can really use reservoir engineering to adjust parameters such that you drive the velocity field and the Bloch vector dynamics inside this equatorial plane. And this velocity field is now very nice to visualize what's going on in this Pontus-Mpemba effect. So on in this plot, you see this is the R1, R2, so that's the equatorial cut of the Bloch ball. And the velocity field has a direction which is indicated by the arrows. And it's the size of the velocities indicated on a color scale. So if it's very small, then it's red. If it's fast, then you have a very a more bluish or green color. Yeah? So that's a plot of this velocity field for this case. And now we choose a situation where this is the initial state. This is our final target state, which we want to reach. Here we have an auxiliary state, and here we have an intermediate state. So let's first couple the system to the environment, driving it to F. Then you get this velocity field. For the environment driving it to A, you get this velocity field. So the direct system copy, which would be the trajectory from S to F, shown as blue curve here, we see that this direct protocol, so our system copy 1, it has to traverse a slow velocity region. So it will take a long time in the direct route to go from S to F. So the strategy here is, it's much better to first go from S to I. This is a fast region. And then once you shouldn't go all the way to A, then you will run into a slow region again. This you don't want. You have to decouple at some point around here. At that point you switch, couple to this environment. So you have to go back to this panel. And then you propagate along this curve again through a fast region to F. And the total time for going from here to here plus here to here will be much shorter than the time for going from here to here. Even though the length looks like it's a disadvantage, the color scale tells you this is fast and this is fast, while this will be very slow. And so this velocity field can really help to see when it pays off to make a detour around these low regions. What you have to avoid is these low regions. You need to propagate around this. Yeah? And of course, the trajectories are always tangential to the velocity field. Yeah? You see this here, so it follows always along the tangential. But to see the time, you really need the color scale of these plots. Now again, you can classify all possible Pontus-Mpemba effects. They are distinguished again by the behavior of the trace distance curves. And all three cases that are possible are already realizable for n equal 2. And we distinguish a weak type A, a weak type B, and a strong Mpemba effect. Rather than showing you these definitions in detail, let me show you some pictures. So these are for 3 different cases or environmental parameters. So we start at time 0 in the initial state here. The blue curve is the direct protocol ending up at F, and shown is the trace distance. Yeah. So this is the slow relaxation, in a sense, towards this final state as a function of time. Now the indirect protocol is the two-step protocol. So if we go back, oops, this was the wrong direction. We first go along a green curve here from S to I, and then along an orange curve from I to F. Yeah. So in this example, you see that the green curve would describe the trace distance to F if we drive it with the environment A. So of course, then we will end up in A and not in F. And so this would have, in this specific case, it still approaches F initially quicker than the direct route. Yeah? So if we decouple at this point, then the trace distance for the two-step protocol will at all times stay below the blue curve. So it's that's in that case the most advantageous thing you can do. The optimal I would be if you're just at that minimum and then go a switch to the other environment, and so the intermediate state could be chosen here. This would be what we call weak type A. Weak type B would be that intermediate state. In that case, you will have crossings of the trace distance. And if the intermediate state is even further away than the initial state, we say it's a strong Pontus-Mpemba effect. Yeah? Then you basically follow this curve here. In all 3 cases, you are quicker. You see the final approach to F is in all 3 cases quicker by doing the two-step protocol. It could be that if the I state is taken somewhere here, then you lose the Pontus-Mpemba effect. Yeah, but in that case, of course, it's best if you choose it here. Second case would be if the propagation toward A doesn't go below this blue curve initially. In that case, you will not find a type A, but you can find a type B or a strong Pontus-Mpemba effect. And if it's like this, so if you initially move away from F, that's actually what is corresponding to the Pontus example of Aristotle. In that case, you have only the strong Pontus-Mpemba effect. So from the application point of view, the fastest will probably be the weak type A, in which case you could probably achieve the best results. We have also studied a large system, not just n equal 2. So in a large open quantum system, which exhibits so-called dynamical phase transitions. So some time after a quench, in real time, there is a phase transition at some time. Then you can use this fact that there is a dynamical phase transition to systematically enhance these Pontus-Mpemba effects. We have shown this for a dissipative Cross-Neveu model in 1 dimension, and that establishes also interesting connections between this Mpemba physics and the physics of this dynamical phase transition. So if you want to see details, I refer you to this paper or ask me later. And with that, I'm at the conclusion. So the field is just burgeoning right now. If you look on the archive, you will see almost every day a preprint on quantum Mpemba effects. And in particular, what are open issues are theories for non-Markovian systems. One pressing issue is that there is no unified theory for closed and open quantum systems. So these are really using completely different, almost orthogonal approaches right now. And so it would be very nice to have a unified theory that allows to treat everything on one footing. And then, of course, there are zillions of applications that one can study where these Mpemba effects could have some application. Okay, thank you very much.
Okay, good. Let's open for questions. I just want to kindly remind you to use the microphone since we have people joining online.
Okay, just one quick question. Can you comment more on the applications that you mentioned, possible applications?
Yeah, so applications are, for instance, you want to speed up quantum state preparation protocols, and you could use such ideas like performing such multi-step protocols in order to significantly speed up such protocols, yeah? Or even quantum computation or manipulation protocols. So all types of protocols where you do something in real time with your system, you can systematically optimize with these strategies. So the message is there are many cases where the direct approach is not the best because you encounter such slow velocity regions, and if you manage to identify them and then steer your system around those slow velocity regions, you can gain a lot. So you can cool down things. It's probably also for quantum heat engines or quantum devices that operate on such principles. This could be helpful.
Yes. Thank you for the very nice talk. I have two questions, but I have to make a disclaimer because the first one is very, very, very silly. And what is really quantum in the quantum Mpemba effect? Because if we think that our initial state is thermal, so we can assume that it's diagonal in its Hamiltonian, and in principle we could equivalently describe this in terms of a probability distribution, right? Evolving under some stochastic process, so there's not so much.
The quantumness sits in the Hamiltonian here. Yeah, so this equation here, I mean, if you have a closed system, all this is gone. Then you have just unitary evolution, and then there's also quantum Mpemba physics. Yeah.
Yeah.
And in that case, people usually consider a subsystem of a large isolated quantum system, and then sort of the rest of the, apart from the subsystem, is taken as the path for that system. Yeah?
I see.
So that's one possibility, and you have to remember we always operate this in a limit of very weak coupling to the leads. Yeah? So there is a competition between quantumness that comes from here. Mm-hmm. And for instance, these trajectories in the velocity field, they can have spiral motion that comes directly from quantum mechanics and reflects coherence. And quantum correlations can be explicitly seen here. They are really crucial also for these effects.
So this effect won't be generic for arbitrarily Hamiltonians?
The effect depends. I mean, as we have seen, it depends on the shape of this velocity field. And the shape of the velocity field depends on the entries in this Kosakowski matrix and on the Hamiltonian. So it might be that for other choices, this is perfectly the best process that you can imagine. The direct route is the quickest, and there's no need to do anything else. But most typically, what we find, if we just do a random selection of parameters, is it usually pays off to do a detour and go quicker. Yeah.
I see.
Okay, thank you for a nice talk. And the first question, I'm going to make two questions also. The first about if you have like some results about quantum speed limits making a limit to the Mpemba effect. You have something?
That's a very good question. I don't have any, I mean, you probably think of something like Lieb-Robinson bound or something like that. I'm not aware of any, I mean, in the closed case, this has been established. So if it's an integrable system, then people can use this analogy to Lieb-Robinson bounds and have an ultimate speed limit that you could reach. Of course, you cannot reach a time that goes to zero. Right? It will always take a finite time, but what exactly this lower limit is a very good question. I don't know. Yeah.
Nice. And the second is sorry, I forgot the name. Okay, the Pontus Mpemba effect. You have some also the question about some spending of work, like you want to make a two-step process to make it quicker. You can make a two-step process to make it spend less work.
Of course, it might cost more work, but here the gain, I mean, what one wants to optimize is the speed. It could very well be that because you first heat it up, that costs you some work, yeah. But the sun is doing it, so I'm not paying for it. Right. I don't care, yeah. Okay. So of course, work is a different matter. So if you want to optimize work, I would suspect the direct route is always the best. But then you pay with it for slowness. Okay. Yeah? So here the goal is really to be fast, even if you have to pay energy for it or work. For it, and it always depends on what you want to optimize.
Okay, that's nice. Thank you.
Can you okay, that's much better. Can you compare the entropy production as your system approaches the final state for type 1 and for type 2? Like as you are faster, for example, is entropy production for the faster path higher than for the slower path or something like that?
This can very well be. We haven't systematically analyzed this, but this is very well possible. Yeah, so that there is a sort of free energy cost from the entropy production. That in that sense, you have to compensate this gain in speed by paying some energy or entropy. Yeah. That's very likely. Yeah, okay. But we haven't quantified it. But it's an excellent question. Yeah.
So, and the other question is the difference between type 1 and type 2 a fixed property of the system, or does it depend on the metrics you choose?
It depends on the parameters. Yeah, so
but, I mean, on the metric. Because your examples use the Euclidean metric. So if you chose another metric, measure of distance, instead of the Euclidean one, could something that previously was type 1 now become type 2?
No. The distance function in parameter space is simply to say, what do I mean when I say the parameter is closer or further away from the final parameters. And so we have only looked at things that are on a straight line from and then it doesn't really matter. You could just use absolute values or so this measure is really absolutely uncritical. Yeah.
More questions?
Well, thanks for the very nice talk. We were discussing a lot here because we are still not sure about the role of quantumness here, right? Like, because, well, okay, of course you are doing a quantum description with Hamiltonians and like you have dissipation effects and so on and so forth. But so let's say in the qubit case, like coherence plays an important role? Or like other kinds of quantumness, I would say, like some sort of quantum correlations.
Yes, we have monitored that, especially for this interacting Kitaev model, where you don't have a Pauli master equation. In cases where you have a Pauli master equation, you really can cook it down to essentially classical model, because then you just look at the diagonal elements of the density operator, and then I agree. But in this other model, where the unitary dynamics and the dissipative dynamics really directly compete and have different effects, there it's very clear here. We see quantum correlations, and it's very different if we switch off the Hamiltonian and have only the dissipative dynamics, or whether the Hamiltonian dominates. Yeah. So in general, correlations are very important, and we also monitor coherence in that and that scene. Yeah. But it depends a bit on the model. So if you take a very simple model like the Anderson impurity, I agree, then one probably shouldn't call it quantum Mpemba, but it's really almost classical. But in this other model, or in the closed systems where you don't even have a bath, then it's really fully quantum.
Yeah. Thank you.
Okay, more questions?
So is it possible to say in some sense that quantum effects, they enhance the Mpemba effect, or because if they just destroy it, right, then as Raphael and Ali said, that probably it's just purely classical. But
no, we found, I mean, it's both is possible, but typically the quantum correlations help to enhance it. So that's typically what we observe. And that's also what these experiments on ion traps have seen. They use a different distance function called entanglement asymmetry. So basically they take a subsystem, think of a spin chain, take a subsystem and twist those spins by some angle theta. And then at time 0, you change this, let's say, a short magnetic field only acting on those back, and wait or measure how long it takes till they relax, or till the symmetry is restored. Yeah. And that's a fully quantum effect. Yeah. That is really related to entanglement and nothing else. Yeah.
Okay, more questions? If not, let's thank Professor Egger again.